Hello, students. Welcome back. In our previous lesson, we explored what chemical reactions actually are and how they happen all around us every single day, like rusting iron or digesting food. But today we're going to learn how scientists represent these chemical reactions using chemical equations and why balancing those equations is so absolutely crucial. We're jumping right into Chapter 1 of Class 10 Science. Let's get into it. Here's our roadmap for today's explainer. We'll start with the language of chemistry, then map out reactants and products, look at the conservation of mass law, learn how to balance chemical equations, check out states and conditions, and finally wrap up with a quick revision and practice. Easy, right?
All right, part 1, the language of chemistry.
So imagine a teacher asks you what happens when magnesium burns in oxygen. You could write a long, drawn-out sentence, magnesium reacts with oxygen to form magnesium oxide. And hey, that's completely accurate. But think about writing out those massive sentences for thousands of chemical reactions. It would take forever. Scientists needed a much simpler, more universal language.
And that language is the chemical equation. Look at the difference here. Instead of that clunky word equation, we use symbols and formula. Mg plus O2 yields MgO. It's so sleek. And the best part? It doesn't matter what language a scientist speaks, whether they're in Tokyo or Paris, they can look at this exact equation and instantly know what's going on. It really is the universal language of chemistry.
Moving on to part 2, reactants and products. Now, every equation tells a story of transformation, moving from left to right. The substances present before the reaction takes place, the starting ingredients on the left side, are called reactants. Here are magnesium and oxygen are the reactants. Then the arrow points to the new substances formed after the reaction, which are our products. In this case, MgO is the brand new product. So just remember, left side equals reactants, right side equals products.
Let's hit section 3, the conservation of mass law. But wait, let's actually count the atoms in our magnesium reaction. You're going to spot a major issue here. On the left side, we have 1 magnesium atom and 2 oxygen atoms. But on the right side, our product only has 1 magnesium atom and 1 oxygen atom. Think about that for a second. We started with 2 oxygen atoms and ended with 1. That means an oxygen atom just vanished. The equation is unbalanced, and in chemistry, that is a huge problem.
Why is it a problem? Because nature strictly enforces the law of conservation of mass. This fundamental law states that matter can neither be created nor destroyed during a chemical reaction. Atoms can't just disappear into thin air. They only rearrange themselves, so the number of atoms before and after a reaction absolutely must be equal. To make them equal, we have to balance the equation.
Which brings us to section 4, balancing chemical equations. So how do we actually fix this mathematically? We place what's called a coefficient, a number in front of the formula, to multiply the atoms. If we put a 2 in front of our MgO product, boom, we now have 2 oxygen atoms on the right, matching the left. But wait, that 2 also applies to the magnesium. Now we have 2 magnesiums on the right and only 1 on the left. So we just jump back over to the left side, put another 2 in front of the Mg, and look at that, 2 magnesiums and 2 oxygens on both sides. We now have a perfectly balanced equation. 2Mg plus O2 yields 2MgO. Now, listen to me very carefully, because this is the single most important rule you will learn today. You can only add coefficients in front of the formula. You must never, ever alter the chemical formula itself. If you need more oxygen, you cannot just change O2 into O3 or MgO into Mg2O. O2 is the oxygen we breathe, and O3 is ozone, a completely different toxic gas. So keep your hands off those tiny subscript numbers. Only use big coefficients in the front. Whether you're balancing our magnesium example or something like hydrogen and oxygen forming water, you can always rely on this simple 6-step checklist. First, write the correct formulae. Second, count the atoms of each element. Third, compare both sides. Fourth, add suitable coefficients. Fifth, recheck the entire atom count, because fixing one thing often changes another. And step 6, confirm both sides are equal. Stick to these steps, and you'll nail it every single time.
All right, section 5, states and conditions.
Knowing the substances is great, but scientists often need to know their physical state too. We add these tiny symbols in parentheses next to the formulas: S for solid, L for liquid, G for gas, and AQ for an aqueous solution, meaning dissolved in water. Take a look at our water example. By adding these state symbols, we instantly see that we're reacting gases to create a liquid product. It just adds so much clarity to the whole story.
And sometimes reactions are incredibly picky. They need special conditions to actually happen, like intense heat, a jolt of electricity, or a catalyst. We write these conditions right above or below the arrow. For example, breaking down calcium carbonate requires heat, so scientists just drop that little delta symbol, the tiny triangle, above the arrow. It's exactly like a recipe telling you what environment is needed to cook up the reaction.
So, why go through all this trouble? Well, balanced equations are the whole foundation of chemistry. They help scientists understand reactions correctly, calculate exact quantities of substances, and perform lab experiments safely. Without them, studying massive industrial chemical processes would be impossible. Basically, without balanced equations, chemistry would just be confusing and inaccurate guesswork, and we definitely don't want that.
Finally, Section 6. Quick revision and practice. Let's do a quick recap. Today, we figured out what a chemical equation is and why sleek symbols beat long word equations. We learned about reactants on the left and products on the right. We saw how the law of conservation of mass means atoms can never be destroyed, which is exactly why we use those 6 steps to balance equations using coefficients, never changing the formula. And we wrapped up with physical state symbols and reaction conditions. You've now got the foundational tools to read basically any equation out there.
All right, practice time. Can you balance this equation? Iron plus oxygen yields iron 3 oxide, also known as rust. Fe plus O2 yields Fe₂O₃. Pause this explainer right now and try applying our 6 steps. Write your final answer down in the comments section and let me know which part of balancing equations you found the most interesting. Also, just imagine a universe where the law of conservation of mass didn't exist, where matter could just vanish into nothing. How incredibly chaotic would our world be? Think about that. Keep learning, keep practicing, and I'll see you in the next lesson.